Hey everyone, my name is Nathan, and over the course of the summer, I will be going through the AP Calculus curriculum. So if you're looking to get a head start in this next school year, prepping for the AP exam, or you're a parent who forgot everything they learned in high school and wants to prove to your 12-year-old son that you're better at math than them, these videos are for you. Throughout this video, there will be moments when I ask you to freeze and pause your video. I'll be going through the material at a pretty fast pace, so it's important that you take these moments to check your understanding and try to answer the questions I provide. Let's get started. Today we're going to be talking about limits. Limits are one of the most fundamental ideas in calculus and form the basis of many advanced topics in mathematics. We're not going to worry about all those yet, but it's important to have a really strong understanding of limits before we dive into all the other calculus topics. So, what is a limit? Well, let's start off with a limit that you're probably pretty familiar with, the speed limit. Now, for the sake of argument, pretend we live in a world where people actually follow the speed limit instead of driving 90 on the freeway and cutting me off every time I try to merge. Anyways, suppose we were to record the speed of every car on a road. I bet you could tell me what the speed limit is. Even if the cars never actually reach that speed limit, let's say we record speeds of 40, 42.5, 43, 44.6, and 44.8, you would be able to tell me that the speed limit is most likely 45. The same idea holds for mathematical limits as well. A limit is a value that you get really, really close to as you approach a certain destination. Let's take a closer look. There are three parts to a limit. First, we have to know what we are finding the limit of. You can find the limit of a function, a sequence, a series, or pretty much any mathematical expression. We'll start off by evaluating the limit of a function. Let's say f of x equals 3x plus 2. The next part we need to know is where we are finding the limit. Our function is written in terms of x, so let's find the limit of f of x as x approaches 4. Finally, we need to find out what the limit is. Looking at a graph of f of x will help. Starting from the origin, let's move across the x-axis towards x equals 4. We see that as we get closer and closer to x equals 4, f of x gets closer and closer to 14. Now let's start from x equals 8 and move to the left. Just like before, as x moves towards 4, f of x goes to 14. We can now conclude that the limit of f of x as x approaches 4 is 14. It's important to remember that in order for a limit to exist, it has to be the same coming from both sides. Imagine two cars driving towards the same address from opposite directions. Even if they arrive at the same place, they won't be able to meet each other if they're at different elevations. This is where the idea of one-sided limits comes in handy. In the example we just did, we looked at the limit as x approaches 4 from both sides. However, maybe one side of the function is ugly and we only want to look at the other side. I'm just kidding, all functions are beautiful. But sometimes we do want to look at the two sides independently. So we use plus to denote a limit that is approached from the right side, and minus to denote a limit that is approached from the left. Suppose we had the following piecewise function. If we approach 0 from the right, we reach a limit of 2. If we approach 0 from the left, we reach a limit of 1. Even though f of 0 is equal to 2, since f of x gets arbitrarily close to 1 as the negative x values approach 0, our one-sided limit from the left is 1. Clearly the two-sided limit as x approaches 0 does not exist, but our one-sided limits still give us a good look at the behavior of this function. One reason why limits are so helpful is that we can evaluate the limit of an expression as it moves towards
infinity and beyond!
For a function, instead of approaching a specific x value, we're just going to keep moving down the x-axis to the right forever and ever. Of course, you're never actually going to reach infinity. Trust me, I've tried. It's not worth it. So we're going to have to know something about the behavior of a function in order to know where it will eventually end up. Let's take a look at the function f of x equals 4 times 1/2 to the power of x. Following the graph as we move towards positive infinity, it looks like the function is getting close to 0. Now the question is, will it ever actually hit 0? Will it go below 0? Look back at the function. We see that every time x increases by 1, f of x is cut in half. Since we started at positive 4, we know that f of x will never be negative. We also know that no matter how small a number is, it can always be cut in half. It's kind of like that one corner of your shower where no matter how much you scrub it, it never gets completely clean. So, even though f of x looks like it should hit 0 at some point, it never actually will. This is where limits will come in handy. I mentioned before that as long as f of x gets really, really close to a certain number, even if it never actually reaches that number, a limit can exist there. Since f of x will get arbitrarily close to 0 as we move farther and farther down the x-axis, we can say that the limit of f of x as x approaches positive infinity is 0. The same thing can be done with negative infinity. In this example, if we keep moving left along the x-axis, we see that f of x gets bigger and bigger. From our table, we know that each time x decreases by 1, f of x is doubled. Since it will continue to get bigger no matter how far we go in the negative x direction, we say that the limit of f of x as x approaches negative infinity does not exist, or that it equals infinity. Let's do a quick recap of everything we learned. First, let's look at the official College Board definition of a limit. Given a function f, the limit of f of x as x approaches c is a real number r if f of x can be made arbitrarily close to r by taking x sufficiently close to c, but not equal to c. In our first example, c was 4 and r was 14. In the example we just did, c was infinity and r was 0. Next, we showed you that you can take limits going from the left and the right side of a function independently. Lastly, we learned that we can take limits at positive and negative infinity by predicting the end behavior of a function. Next time, we'll talk about different strategies for finding a limit and the algebraic properties of a limit. If you like this video, please give it a thumbs up or subscribe to my channel. It really helps out a lot. Let me know in the comments if you have any questions or if there are any specific problems you want to go over. Good luck out there, and I'll see you next time.